Let's work on this probability distribution. We roll a six-sided die 3 times and we count the number of 4s. So we're going to later identify this as a binomial distribution, but at this moment, I just want us to view this through the lens of we have to find our events and then we have to find their probabilities. We're not going to give ourselves the binomial equation just yet. In fact, this is a small enough problem. We're only rolling this die 3 times. I think we can count all the events. So first question is, what are the events? So if you're flipping 3 times, you don't really care about what is on the die, right? If you get a 2, a 1, and a 4, because we're just counting the number of 4s. So that right there would be, we've got 1 4. So if we just are interested in counting the number of 4s, you could roll 3 times and none of them be 4s. One of them could be a 4, 2 of them, or maybe all 3 rolls give you a 4. Right? It's going to be unlikely, but still possible. In fact, let's figure out how unlikely things are. Let's give the probabilities of each of these events. So we're flipping 3 times, and we're interested in if it's a 4 or not. So the probability of a 4, if it's a fair die and there are 6 sides, then a 4 is one of those 6 sides. The probability of not a 4 would then be 1 minus 1/6, or 5/6. That kind of looks like an O. It's supposed to be a C for complement. Well, that wasn't better. C. Okay, so we flipped the die 3 times, and we're interested in 0 4s. So not a 4, not a 4, and not a 4. What are the probabilities of this happening? So this is the probability of an intersection. You need not a 4 to happen first, and there's a 5/6 probability of that occurring. And you need a not 4 on the second roll, and you need a not 4 on the third roll. When you go through this, you get 5 cubed over 6 cubed. That's going to give you 0.5787, or 57.87%. All right, so the probability of not rolling any 4s is if we have 3 not 4s in a row. That's, let me zoom in. 5 cubed over 6 cubed. 0, oops, let's give it as a percentage. 57.87%. So odds are good that we roll 3 times and we don't get any 4s. All right, let's clear off the board and talk about the second event. How many ways can we get 1 4? In fact, you've got these 3 different positions. So how many ways can you put one single 4 right there? You're choosing where to put the 4, right? And it's a choose equation because you don't care where the 4 happens. The order of the 4 doesn't matter. You just want there to be one of them. In fact, let's go ahead and list out the events. One of them will be a 4, and then not a 4, and then not a 4. Another one will be not a 4, and then the 4 is your second roll. And then finally, the other way to get 1 4 is to roll it at the very end. But all of these have the same probabilities. The probability of a 4 on the first roll is 1/6. And we need a not 4 on the second roll. And we need a not 4 on the third roll. The second way to get a single 4 in 3 rolls is not 4, 4, not 4. The third way is not a 4, not a 4, and then our 4. But due to the commutativity of multiplication, the order of these don't matter. So we all get the same thing. We get 0.1157, right? For every situation here. So either of these three cases will satisfy the condition of rolling 1, 4. So that's a probability of a union, right? It could be this case, or it could be this case, or it could be this case. So there's three different ways to do that. 3 times 0.1157 gives us 0.3472. So in this case, the event of rolling 1, 4 across 3 rolls, it was 5 squared over 6 cubed, right? If you go over to all of these, every single row has 2 5s, and then the 1 doesn't matter because it's multiplicative identity, but we still have 3 6s down in the denominator. Oh, but then I have to multiply by 3 because there's 3 ways to do that. And we get 34.72%. Okay, let's think about the next event. We're flipping 3 times and we're counting 2 4s. So you're going to see a lot of similarity between this and what we just did. All right, we have multiple ways to get 2 4s across 3 rolls. So we're going to have to count how many ways there are to do that and then add their probabilities together. If I'm putting 2 4s in 3 rolls, it could be here, here. Oops, they're not 2s. They're 4s. So maybe a 4, and then not a 4. Or maybe a 4, not a 4, and then a 4. Or maybe not a 4. Oh wait, where was my not a 4 up here? Not there. So either the not 4 is in the last position, in the second position, or in the first position. So there's 3 ways to put 2 4s in 3 spaces, right? You can run through your choose equation and you see that 3 choose 2 is equal to 3. So for the same reasons that we've already discussed, all of these have a probability of that's a 4, that's another 4, and not a 4. You get 0.1, oops, no, 0.023, messing up, 0.0235. Right? And there's 3 different ways for that to happen. So 3 times 0.0235 gives us 0.0694. So back to our table. The probability of getting 2 4s across 3 rolls is 5 divided by 6 cubed, right? In all of these cases, we only had 1 5 in our numerator, but still 3 6s in our denominator. And there were 3 ways to do that. So we get a probability of 6.94%. All right, so notice the symmetry here. There was 1 way to get 0 4s. There were 3 ways to get 1 4. There were 3 ways to get 2 4s. There's going to be 1 way to get 3 4s. In fact, we don't have to list out all, well, we will list out all the events. We'll list out the only way to do that. The only way to get 3 4s in 3 positions is a 4, a 4, and a 4. They all occur with a probability of 1/6. So we need a 1/6 to happen, and then another 1/6, and then another 1/6. This probability is 0.00463. And there's only one way to do that, so that is the probability. So it's 1 over 6 cubed. All right, we didn't have any 5s in our numerator over there. Gives you 0.463%. And as always, a good way to check yourself that you actually did count all the events and your probabilities on your right-hand side of the table is correct, is to add them up. And I think we did everything correctly because I get a sum of 100% on my right-hand side. So again, this is what we'll later call a binomial distribution. At this point, it's kind of tedious to write out all the events, but I think it's beneficial to see at least once.